In this video, we will now be looking at how random walks link to financial physics. This video follows the mathematics of the YouTube series, Financial Derivatives, which has been created by the channel, Maths Partner. In the previous video we looked at how fluctuations in price link to Brownian motion. But now we will look at how they are also centered around the idea of random walk. This means that future changes cannot be predicted with certainty based on past movements. If we consider a symmetric random walk denoted by xn, with an even probability of p equals half, the value of the process either increases or decreases by 1 with each discrete time step. This can be modeled as the summation of zk, where zk is the root of t over n, the time interval split into n equal periods. Plotting a graph of xn against t shows the random walk in the discrete case, where the time intervals are definite. Different time intervals can be used, and as the steps get smaller, and tend to zero, it is now a continuous case. Brownian motion has been established to be continuous, so can be considered as a random walk with very small intervals. The expectation value of zk can be found to be 0, because the random walk is symmetric with a probability of half, to either increase or decrease by 1. So zk can be expected to remain roughly the same. The expectation value of zk squared is t over n, the time interval divided by the number of steps. As the sum of zk is equal to xn, the expectation value of xn is also 0. Using the rule that the expectation value of two different variables is 0 as shown, it can be found that the expectation value of xn squared is t. Pause the video now and have a go at proving this. Xn has already been defined as the summation of zk, so can be replaced with that in the expression. Since we are dealing with xn squared, and hence the summation of zk squared, we can expand the brackets. As we know that the expectation value of two different variables is 0, these terms can be cancelled in the expansion, leaving only the z squared terms. The expectation value of zk squared has also already been defined as t over n, so the summation of all of these up to the nth term leaves an answer of the expectation value of xn squared as t. We have therefore shown that in the discrete case, the expectation value of xn is 0, and the expectation value of xn squared is t. As these two expectation values are independent of the value of n, the number of time steps taken, they are also true for the continuous case, where n tends to infinity, so therefore are also true for Brownian motion, which takes the value bt. Therefore, the expectation value of bt can be said to be 0, and the expectation value of bt squared is t. It can therefore be said that Brownian motion remains finite, or bounded, as the expectation values don't tend to infinity. Brownian motion is a Markov process, meaning it is memoryless, so it doesn't matter what comes before. And Brownian motion is a martingale, which means the best guess for the future is what is happening now. We will explore this in further detail now. Martingales are a zero-drift stochastic process, so the mean doesn't change and remains as 0. The mean can be defined as the expectation of a random variable, with the expectation value of the modulus of a variable xn being less than infinity. This corresponds to the share price, for example, which couldn't tend to an infinite value, and must be contained within a finite amount of time. The principle of the martingale can take the form as shown on the screen, where m is less than n. The right-hand side of the bracket represents all of the available data, with today's value being xm and tomorrow's value as xn, which is predicted to be just the same as what happened today. This demonstrates that whatever has happened in the past will be the same as in the future, and this principle can be used in finance to make money. As has already been established, share price S follows Brownian motion. It would be expected that the share price would grow exponentially, which could be modeled in the form displayed on screen, where S0 is the initial share price, and alpha is the rate of growth over time t. However, the share price actually grows in a jagged motion, although still following the shape of a standard exponential. This geometric Brownian motion is therefore modeled by the form on screen. The extra term in the exponential accounts for this jagged growth. The constant beta is very important in finance, with entire industries dedicated to measuring it. This model can be rearranged to the new form displayed by taking logs. The alpha t term will contribute to the mean, but the mean of the beta bt term is 0 because standard Brownian motion bt is normally distributed with mean 0 and variance t. Alpha t plus beta bt will also be normally distributed, but not with a mean of 0 or variance t. Instead, alpha t plus beta bt is normally distributed with a mean of alpha t, and a variance of beta squared t. The variance is obtained following the general rules shown. From the obtained log model, the alpha t plus beta bt distribution can be rewritten as shown. This ratio of the share price at time t is known as the log normal, where the log normal curve is a skewed normal curve. Geometric Brownian motion will follow the jagged exponential model that we have just explored, and serves as a fundamental principle in financial physics.